Welcome back to the deep dive, ready to explore another corner of the AI world. Today, we're looking at something that really caught our eye, a paper that basically asks, do we really need normalization in transformers?
Yeah, it's one of those things, you just kind of take for granted in modern neural networks. Like, it's just there. Normalization, gotta have it. But this research really throws that into question.
Especially in transformers, right? They're everywhere, layer norm, RMS norm, all that.
Exactly. And they're thought to be essential for stable training, avoiding those exploding gradients, helping models converge faster. Batch normalization, that was the real game changer back in 2015, right? It kind of set the stage for this whole normalization wave in deep learning.
And then with transformers, layer norm just became the standard. You normalize across the sequence dimension,
Yep.
keeps everything nice and well behaved during training.
Right, and RMS norm, that's another one that's become popular, particularly with those huge language models. But the underlying assumption has always been, well, you need some form of normalization to make these complex architectures train effectively.
So to see a paper that challenges that head on is, well, it's pretty exciting. And they don't just poke holes, they actually offer a potential solution.
Yeah, a surprisingly simple one, too. It's called Dynamic TON, DYT for short. And the crazy thing is, it seems to work. Like, across a wide range of tasks, it can replace those normalization layers, and the models perform just as well, sometimes even better.
So our deep dive today is all about unpacking this dynamic ton. We're going to go through the paper, Transformers Without Normalization, see what they did, what they found, and what it all means. For those of you out there wrestling with transformer models every day, this is definitely something you'll want to pay attention to. Could be a game changer.
It could be. So, to jump right in, the authors started with a pretty insightful observation. They were looking at these trained transformer models, and they noticed that the input-output behavior of layer norm, it often looked a lot like a TON function, that classic S-shaped curve.
The layer norm wasn't just like linearly scaling things, it was also kind of squashing those extreme activations.
Exactly, and that got them thinking, well, what if we just did that directly? What if we had a simple operation that did that scaling and squashing without all the overhead of calculating those activation statistics? And that's how Dynamic TON was born.
Okay, so let's break down DYT. What is it like at its core?
It's really pretty straightforward. You have your input activations, call it X, and you have a single learnable scalar parameter, which they call X. So you multiply your input by X, and then you just take the ton of that. DYTX equals ton of X times X. That's it.
So no more calculating means and standard deviations for each batch or sequence like you do with layer norm. Just one global scaling factor, and then the tan function does its thing, squashing those values between -1 and 1. Seems a lot more efficient, computationally.
Much more. And the way they designed it, DYT just slots right in where those normalization layers used to be. You can see it in figure 1 of the paper, those nice little block diagrams. It works in the attention mechanisms, in the feed-forward networks, even right at the output layer.
Elegant, huh? But does it actually work in practice? That's the real test.
Well, that's where things get really interesting. They didn't just test it on one or two toy problems. They threw it at a whole range of tasks. Supervised learning and computer vision, self-supervised learning, image generation, massive language models, speech recognition, even DNA sequence modeling. And the results are, well, they're pretty impressive.
Let's start with vision. What happened when they swapped layer norm for DYT in those vision transformers and CODNext models on ImageNet?
Take a look at Table 1 in the paper. Across both architectures, VIT and CONNEXT, at both base and large sizes, DYT either matched or slightly exceeded the top one accuracy of layer norm on ImageNet 1K. And it's not just the final performance, the training dynamics seem to be similar too. Figure 5 shows the training loss curves for the base models, and they're basically right on top of each other, whether it's DYT or layer norm.
So it's not just that it works, it's learning in a similar way. What about self-supervised learning in vision using things like MAE and DIO?
Same story. Table 2 shows those results. They used DYT with VIT backbones for both MAE and Dino, and they were consistently on par with the layer norm versions in terms of ImageNet fine-tuning performance. So whether you're reconstructing images like in MAE or doing contrastive learning like in Dino, DYT seems to be a good replacement.
And what about those big generative models, those diffusion transformers? Do they test it on those too?
They did. They looked at DIT, diffusion transformers, for image generation. And again, the results in Table 3 show that DYT either matches or slightly beats layer norm in terms of FID scores, which is a common way to measure the quality of generated images. One interesting thing to note here is that in DIT, those affine parameters, the gamma and beta from the normalization layers, they're used to incorporate class conditioning. So when they swapped in DYT, they kept that same setup, just replacing the normalization part itself. Shows how adaptable it is.
Okay, but the really big one, the one that I think has everyone's attention, is the large language models. They actually went and pre-trained llama models, those massive multi-billion parameter things, using DYT instead of RMS norm. That's a serious undertaking.
It is, but the results are, well, pretty compelling. They trained llama models ranging from 7 billion to 70 billion parameters on the Pile dataset, 200 billion tokens. That's essentially the same recipe as the original llama models, just with DYT instead of RMS norm. And as you can see in Table 4 and Figure 6, the training loss curves are basically identical between the two across all those model sizes. And when they tested the pre-trained models on a whole bunch of zero-shot tasks from the LMeeble benchmark, the average performance was, well, essentially the same.
That's kind of mind-blowing. But they did have to make a couple of adjustments when using DYT for LLMs, right?
Yeah, two key things they found. First, they need to add a learnable scaler right after the embedding layer. Without that, the activations at the start of the network were just too small, and the model didn't learn effectively. It's kind of interesting, actually, because the original transformer architecture, it has a fixed scaler in that same spot. And second, they found that they needed to be really careful about the initial value of that OS parameter in DYT, especially for these huge models. We'll get into that a bit more later.
Okay, so vision, language, it works there. But what about other areas, like speech or even something like DNA sequence modeling? Does it hold up there?
Seems so. They tested it on Wave2Vec 2.0 for self-supervised speech recognition. Table 5 shows those results. The validation losses on LibreSpeech were basically the same, whether they used layer norm or DYT for both base and large model variants. And for DNA sequence modeling, they looked at models like Hyena DNA and Caduceus on the genomic benchmarks. Again, Table 6 DYT was right there with layer norm in terms of performance. So pretty versatile, right? Across all these different domains, it just seems to work.
Okay, so it works. That's great. But what about efficiency? Does using DYT actually make these models faster? That would be a huge plus.
Well, they did some preliminary benchmarks running a Llama 7B model on an NVIDIA H100 GPU with BF16 precision. The numbers are in Table 7. And yeah, they saw some promising improvements. The DYT layers themselves were significantly faster than the RMS norm layers they replaced. The overall speed up for the whole model was more modest, like 8% faster inference time. But a 52% reduction in the latency of those specific normalization layers, that's definitely something to take note of.
Yeah, that's pretty significant.
Yeah.
So not only does it perform well, it has the potential to be faster too. Now, they also did some kind of digging into the inner workings of DYT, right? Like what's really going on there with that TAN function, that parameter.
Right. They wanted to understand why it works so well. So they did some ablation studies, messing around with different parts of DYT. First, they tried replacing con with other functions like hard ton, sigmoid, even just getting rid of the squashing altogether and using the identity function. The results are in Table 8. And what they found was that, yeah, you really need some kind of squashing function for stable training. When they used the identity function, the models just diverged. And among the different squashing functions, good old TON seemed to perform the best.
Makes sense. It's smooth, it's centered around 0. It just seems to play nicely with these models.
Yeah, that's what they speculated too. Then they tried removing the learnable OMP parameter while keeping the different squashing functions. Table 9 shows those results. And across the board, performance dropped when they got rid of ON. So it's clearly doing something important.
So it's not just about the squashing, it's about that learnable scaling factor too.
Yeah.
And they looked at how OMP behaves during training, right? Like how does it actually evolve?
Yeah, Figure 8 gives you a nice visual of that. They found that during training, the IO in each layer, it kind of tracks the inverse of the standard deviation of the activations in that layer. As the spread of activations changes, I adjusts itself, and when the models are fully trained, there's a strong correlation between the final values and the inverse standard deviation of the input activations to those layers. So it's like it's learning to normalize the input, but in a global way, for the whole input, not for each individual element.
Interesting. So Aya is doing its thing, keeping those activations in check, and then the TON function comes in and squashes any outliers. Now, they also compared DYT to other methods that try to train transformers without normalization, right? Like, how does it stack up against those?
Yep, Table 10 lays it all out. They looked at techniques like fix-up, skip-init, those are initialization-based methods, and then there's reparam, which is based on weight normalization. The thing with these methods is they often need a lot of hyperparameter tuning, especially the learning rate, to work properly. So the researchers did a bunch of learning rate tuning for all those methods to make sure it was a fair comparison. And the result, well, DYT consistently outperformed all the other methods across different VIT-based tasks, even after they'd optimized the learning rates for the other approaches.
Pretty impressive, huh? It's not just a toy idea, it actually seems to be a robust alternative to normalization. Now let's go back to that initialization of AF for a minute. You mentioned that it was particularly important for those large language models.
It was. They found a big difference between smaller models and those LLMs. For most of the non-LLM tasks, the final performance wasn't that sensitive to the initial A value. Figure 9 shows that. A default of 0.5 worked pretty well, except for supervised VITL, which could get a bit unstable with a high initial A. But for the Llama models, they had to be much more careful. Table 11 shows the optimal A values they found for different llama sizes, and what they saw was that larger models needed smaller initial A values. Also, they found it was best to initialize ACK a bit higher in the attention blocks compared to other parts of the network, like the feed-forward networks. Figure 11 illustrates that. And interestingly, it seems to be the width of the model that matters most, not the depth. Table 12 shows that. They think this sensitivity in LLMs might have something to do with their massive width compared to other types of networks.
So a lot of nuances there, but the takeaway is you got to be careful with that initial eggs, especially when you're dealing with these behemoth language models. Now, they did mention some limitations of DYT, right? Like where does it fall short?
Yeah, there was one area where it didn't quite work as well. They tried replacing batch normalization in classic convolutional nets like ResNet 50 and VGG19. And as you can see in Table 15, performance took a hit when they did that. Their guess is that it's because of the sheer number of BN layers in those architectures. Batch norm is applied after almost every weight layer, whereas in transformers, normalization, or DYT, is used more sparingly. So DYT might be a better fit for architectures where normalization isn't as densely packed.
Okay, so maybe not a universal replacement for every kind of normalization, but still a pretty significant finding. So to wrap it all up, what's the big takeaway here?
I think the main message is that transformers, they can actually achieve really strong performance without needing those traditional normalization layers. This dynamic TON, it's a simple idea, but it seems to work really well. It learns a dynamic scaling factor, uses a TON function to squash things, and you get comparable, sometimes even better performance than layer norm or RMS norm.
And it could lead to faster models, more efficient models, which is, always a good thing. Plus, it really makes you think about, well, what other assumptions we have in deep learning that maybe we shouldn't be taking for granted. Like, if something as fundamental as normalization can be replaced by something this simple, what else is out there?
Exactly. It's all about challenging those assumptions, seeing if we can do things better, simpler, more efficiently. And for those of you listening who want to really dig into the details, check out the project page and the code. They've got all the experimental results, implementation details, everything. It's definitely worth a look.
Absolutely. So that's our deep dive into dynamic TON and the quest for normalization-free transformers. Let us know what you think, and we'll see you next time for another exciting exploration of the AI world.